It should be about 18 slides or 16 slides. The main focus for me is it's a big learning presentation. This is more theoretical. I will even declare that my engineering background, they actually explain to us that you shouldn't focus on theoretical detail ever. So my whole bachelor's degree, whenever I did a presentation, it was more of like the results and how it related to the real world. And so this is actually my very first like real critical theoretical presentation. So I am more than happy to take your professional criticism, and we can use that to better my presentation in the future when it comes to this type of material. So, yeah, like Dr. Kilin had mentioned, if it comes down to questions, it's probably best to do it in the chat room. I will give him permission, and I'll say Dr. Rasulev, maybe even Dr. Han, they can interrupt me if they would like during the presentation. But I would guess most of the other questions should be done in the chat room, okay? So this is the start of it. So time-dependent excited state molecular dynamics methodology by me. Okay. The main work, or excuse me, the main topics that I'm focusing on come from a paper from 2013 done by Dr. Kilin and other members of the University of South Dakota. And particularly, it's the time-dependent excited state molecular dynamics of photodissociation of lanthanide complexes for laser-assisted metal organic chemical vapor deposition. Once again, the main focus is just the methodology they used. In general, they used ab initio molecular dynamics. Excuse me, the ab initio molecular dynamic algorithm was modified for treating time-dependent excited state molecular dynamics. And we'll be getting into more detail. So just as a conceptual, visual, 2D representation to get the solid concepts, I'm using these figures to explain that in this far left figure, the center circle is supposed to represent an atom, and the outer circles that you see are representing orbitals. The green orbital is supposed to represent an occupied with an electron, and the yellow is supposed to represent unoccupied. So with the inclusion of energy of inclusion of light energy, or light energy, we can excite the electron from a lower orbital into a higher orbital, as you can see from this part of the figure. And then once the energy is removed, de-excitation occurs, and it goes from a higher orbital back down to a lower orbital. This process, which is in this part C of the figure on the right, shows it goes from ground state to excited state, from excited state to ground state, and this process is repeated. In this case, it goes from a lower orbital to a higher, and from a higher back down to a lower orbital. The TDESMD method is different compared to previous methods done, such as just regular molecular dynamics, where it's all stays within the ground state, or excited state molecular dynamics, where an electron is able to go to the excited state, but then stays there rather than comes back down. So the detailed, this figure was actually, I was given permission by Dr. Kilin to use this. I have to give him the proper reference. And so in the far left figure, it's just a schematic diagram of the sequence stimulated absorption and emission events, similar to the previous slide I had just shown. In the middle, we have differing wavelengths, and this would kind of this would show the, say, energy inputted into our system, similar to, once again, what I previously mentioned, but in a different format. So, for example, the blue stands for the ground state population. The red lines stand for the excited state population. This green section here is the electric field, and the black line covering the green field would be the envelope. And what this is kind of showing us is through this constant wave irradiation, which is part B, relative to part C, which is a sequence of pi pulses, is we do see difference in the electronic energy from a constant wave to this, let's say, pulse motion. This pulse, which is actually supposed to be representing light by this oscillation of this electric field, which will give us our, let's say, moving fragments, which will give us differing electro and ionic dynamics throughout our simulation. Okay. Yep. I'm just making sure I've mentioned everything. Yep.
May I ask you to draw a connection between previous slide number 3 and present slide number 4. In previous slide, you do have blue and red lines for the ground and excited state potential energy surfaces. Correct?
Okay. Yep.
In slide 4, middle panel B and panel C, you have blue and red lines that are denoted as rho EE and rho GG. Is there any connection of this rho EE, rho GG and ground and excited state potential energy surfaces on the previous slide?
The oscillation, as you can see in like part, well, actually, we'll focus on part C. So on part C, we'll see that the density matrix increases for the ground state population, and this would be able to be represented as in, for example, this TDESMD would actually be in the blue line. So the colors are flipped and switched, but in this case, if you can see that the green ball electron goes into the ground state, that would be represented by this red line having a high density matrix, and then vice versa, whereas the excited state would be increased, and that would represent, in this previous slide, an excited state on the red line. Does that answer your question, Dr. Kilin?
So blue and red are populations of ground and excited state.
Oh, I apologize. I flipped those backwards. I apologize. Blue is correct. The colors are correct. As you can see, blue is the ground state, and red is the excited state. I apologize about those. So, can you re-ask that question, Dr. Kilin?
No, you already answered it. So okay. Blue is population in the ground state.
Yep.
And red is population in the excited state.
That is correct. Yep.
And as molecule is being irradiated, this population travels between ground and excited.
That is correct.
Oh, okay.
Good. One moment. Okay. So in that paper that I had previously mentioned, we have the algorithm pathway representation, which is kind of formed of different parts. For example, the ionic dynamic parts and the electronic dynamic parts. And I'll do my best to explain the equations involved and approximations we use. But before we actually jump into, let's say, this blue and red section of this pathway, I have to go over the initial information, such as a Rabi cycle and the cone charm orbitals. That is a typo right there, but that's okay. And then we have 5 other assumptions I'll explain at the very end of this presentation. So the first initially is just the Rabi cycle. This is that population and depopulation. So Rabi cycle is a cyclic behavior of a two-level quantum system in the presence of an oscillatory driving field. Once in our case, this driving field would be light, electromagnetic wave of light, and then Rabi theory is used to investigate how periodic perturbation affects the nuclear configuration and electronic structure of the compound.
Not nuclear. Something. I apologize for interrupting.
Please do.
Rabi theory has nothing about nuclear configurations. It's only about two electronic states.
Okay. Okay, well, I'll have to edit that. Okay. So I'll go to the next part. So Rabi oscillations facilitate the charge density transfer between ground and excited states, which is responsible for bond breaking. A little history here about Isidore Rabi is he actually the guy who created the Rabi cycle, or what this cycle is named after. He won the Nobel Prize in Physics in 1944 for his discovery of nuclear magnetic resonance. And just a quick couple assumptions about the Rabi cycle is these are quantized electrons. These are classical description of the electromagnetic field and nuclei as point charges. So the Kohn-Sham equations. This is I'll be showing this figure throughout the rest of this presentation with arrows kind of indicating where we're at. So in this case, Kohn-Sham equation is a one-electron Schrodinger equation, and it is used for, this was kind of developed for a fictitious system, also known as the Kohn-Sham system of non-interacting particles. So to give you some characteristics or understanding of this equation or this system, it generates the same density as any given system of interacting particles. It's defined by an external potential, fake, like I had mentioned, it's a fictitious system to which non-interacting particles move. Particles are non-interacting fermions. Example of fermion would be an electron with half integer spins. And then Ks wave function is constructed from a set of orbitals that are the lowest energy solutions to an eigenvalue equation. Okay, so once again, this is kind of the background information that these two I'm going to say concepts are what's kind of driving this very large methodology that we're using. So to finally jump into the diagram that I had previously shown, we kind of start off with the initial electron density, which is obtained from the sum of products of the Ks orbitals or Ks equations at initial time equals 0, where we have the rho, which is the electron energy matrix. Once again, is the sum of the Ks orbitals. In this case, the phi is the orbital, and the r is the position of the electron density. We then go to, that was the green portion, and in the red portion we have the first, which is the one electron Hamiltonian, which is expressed, which is based on the Kohn-Sham orbitals. So we'll go from the green box into the red portion, and here we have the, I believe it was, yeah, orbital energies, and we have the Bra and Ket notation, which, you have a question, Dr. Kilin?
I can type it.
Okay.
Third line from the bottom, it's just typo. The angular bracket is misplaced. Keep going. I'll type it in.
Okay. Once again, it seems to be the sum of the lowercase indices represents kind of the ground state, and the J is supposed to be the excited state. These are the differing states, whereas upper notation is indicating nuclei or ionic, let's say, characteristics. So once again, going to the next portion, which is the transition dipole, and I'm trying my best to connect everything, but the Rabi frequency, which we've previously discussed a little bit about, is related to the transition dipole and relates the ability of a system to be perturbed by light. So from previous slides, that information is being used for the transition dipole. The transition dipole can be, and is in this case, calculated on the basis of the Kohn-Sham orbitals. We would discuss the equations themselves, which we use the matrix of the transition dipole, and which is equal to the elementary charge of the electron and the orbitals and the position of the electron densities of the initial ground state and the excited state. The Rabi frequency, once again, is related to the transition dipole and intensity of the electric field. But though it is related, it does not come directly from the previous equations. So here I believe this H is the Hamiltonian in polar coordinates. And so the forgot how to say this. I think it's lambda. No, I apologize. What is this unit or this figure? This
symbol.
Symbol. Thank you. What is this?
Can you show by mouse?
This
Omega.
one. Omega. Thank you. So the H bar is the. I apologize. My mouse was on the other screen, and so I thought you guys were able to see it, but it's a different side. So the omega is just the frequency of the Rabi flops, and the H bar that you see is the polar coordinates of the Hamiltonian, which is equal to, once again, the matrices, the transition dipole matrix, and times the electric field.
Why? Let's stay there. So
Okay.
why Rabi frequency is the product of dipole times and electric field? Like what does Wikipedia tells about it, or what you are thinking about it? How does it connect with maybe high school physics?
Yeah. I'm just thinking that in this next slide, I believe
next slide already uses it as an input. So why Rabi frequency is proportional is equal to product of dipole and electric field strength?
What's Rabi frequency? Well, my understanding of frequency is you'd be using a wave, such as sine or cosine, or some sort of, I want to say, oscillation. And so, but then if it's electric field, then that would be like where the frequency comes in, where it goes up and down, and then just the magnitude, which is the transition dipole, that relates once again to the ability of a system to be perturbed by light. So my connection would be oscillation would come from the electric field, but then the transition dipole, which they found to once again relate the ability of a system to be perturbed by light. So those two combined gives us the frequency which we desire.
Okay, so in what you're saying, there is a really healthy thought that if transition dipole is 0, then system is not able to be perturbed by electric field or by optical electromagnetic wave, and there will be no transitions between states, right? Were you saying this?
That, yes, I would believe so.
Okay, so you're claiming that transition dipole is ability of the molecule to respond to electric field, to undergo transitions. And the stronger the intensity of the laser, the larger is the dipole, the better, the quicker are transitions between ground and excited state.
I will agree with you, yes.
Okay. And can you please briefly go back to the slide number 4? Yeah. Looking on the panel B, can you please visually explain where is Rabi frequency? Like if you would be instructor, if you would be instructor in the freshman class, how to explain what is Rabi frequency based on this panel B?
rapid frequency. Well, with any frequency, it's just the time it took for one wave to occur or go
Yep,
through the
yep,
process of one
yep,
wave.
absolutely correct.
Yeah.
So there are two frequencies. The green stripe, if one looks with detail, it shows a lot of oscillations with high frequency, very dense fringes, right?
Oh, yep, yep,
The one that you point with CW.
yep.
And this is high frequency of electromagnetic wave. But it doesn't, the speed, how quickly ground state population goes into excited state is typically much slower than frequency of the incident electric laser field.
Okay.
Okay.
Okay. And so I guess that would be a good comment or question, as we'd say. So in our case, we are trying to, let's say, increase this uh, frequency here, oops, and then kind of shut it off here. Is this true? Or I suppose this electric field is changing
And therefore,
when it's transitioning.
it helps quick transition. Good, good. Another verbal argument is that electric field times dipole, and you can go back to the slide number 9. So electric field times dipole is energy of dipole in electric field, and in some sense it will contribute to the splitting of the energy of the levels, and their splitting is their offset is also related to how quickly they will oscillate between each other, but this is not as colorful. Whew, okay, sorry for interrupting, please continue.
Oh, thank you. So, as previously mentioned, the electric field has some repetition or cosine. The, excuse me. So the optical Hamiltonian, which includes the electric field, which we had previously mentioned, holds some sort of frequency, such as cosine uh, here. And so based on the KS Hamiltonian, which is this figure here, and the dipole interaction with the electric field to describe the transitions from ground state to excited, from excited to ground state. So in this equation, we have the Hamiltonian of the KS, or based on the KS orbitals, which is subtracted by the previously mentioned matrix of the transition dipole and the magnitude of the electric field, plus the Hamiltonian, or the non-adiabatic channel for transitions between electronic and nuclear degrees of freedom, which originates from a matrix element of kinetic energy of nuclei and consists of two terms. So
Meade, do you have non-adiabatic couplings in the calculations that you have completed?
must not, if you're asking
Yeah,
that.
yeah, correct.
Okay. So this particular paper, once again, had focused on the metal and ligand connection, and so this non-adiabatic channel of transitions must be occurring or being used for the metal and ligand experiment that was conducted from this paper. To go further into the non-adiabatic coupling, they specifically look into Bloch equations. So non-adiabatic coupling, also known as vibronic coupling, involves the interactions of vibrational motion between the electronic and nuclear parts of a molecule. In TDESMD, multi-level Bloch equations can be used to find numerical values of the non-adiabatic coupling. In our case, it focuses on the dissipative forces rather than the dissociative. We have, dissipative transitions rather than the dissociative. Once again, this includes the summation of Hamiltonians with the electron density matrix going from ground state to excited, and subtracting that once again from a density matrix times the Hamiltonian going from, it seems to be K to J, from so this above equation needs to be solved, usually done by propagation in small time steps and updating the density with known increments of density.
Meade, may
Yes.
it looks like you are just reading what is on the slides. Is it right?
I know I have a lot of information, but I do have extra that is not shown here. And so the goal of this is to help me kind of explain it to you, but also have a couple tidbits of information on the side.
Okay, it's okay now, but it is not a perfect style. It's
Yeah.
better to everything that what you are delivering verbally doesn't need to be written.
Yeah. Yep.
Okay.
I agree. It's
Okay.
it's
And
usually.
oh, I see there is a question from Yvonne. I'll ask mine and then we'll focus on the one from Yvonne. So you are showing Bloch equation,
Yeah.
and before you were introducing Rabi oscillations.
Yes.
Is there any connection between them?
Yes. My understanding is we're connecting the like vibrational motion, which would be the
Suppose,
product.
wait. Suppose nothing is vibrating. You have only
Oh,
electronic states. So what is the connection between Bloch equation and Rabi oscillations?
mm,
Just make a
uh,
guess.
there's a connection where like Bloch equations themselves. I know they're used for like calculating nuclear magnetization. So I'm thinking of like a connection between like the electrical field and this magnetic field. Okay, and so somehow there's maybe a connection there since it's electromagnetic white light. But
What do
somehow, how is
you,
that actually connecting to Rabi frequency? I don't know. I don't know. I don't know.
do you consider a possibility that by solving Bloch equations, one will get Rabi oscillations? That Rabi oscillations is one of the possible solutions of the Bloch equations.
Yeah, I could consider that. Yes.
Okay. So your main, well, not main, but your technical goal is to see how the population is traveling from one state to another one. This equation is designed to describe such transitions, and Bloch oscillation, Rabi oscillations is one of the examples of a solution when there is a transition between different electronic states, between ground and excited. And there was a typed question from Yvonne. It is related probably to the previous slide. Why non-adiabatic coupling is important or not important for TDESMD?
one moment. So at the first view, non-adiabatic is simply just not occurring without it occurs with heat loss or gain. Okay, so heat loss and is occurring or it's being gained. Okay, so why is that important with TDESMD? Well, it would be, as previously mentioned by Dr. Kilin, it would be an ability to calculate the transitions that are occurring, right? And so this would also include this heat loss or gain throughout these transitions, this energy loss. So that would be my understanding of why it is important.
Okay, so you are telling that are you satisfied or not quite?
Not really.
Let me interpret what Meade told. Let me translate, and maybe it will be sufficient. So Meade told that non-adiabatic coupling opens pathway for dissipation of electronic energy into heat, which means it is different channel of transitions between electronic states that lowers the energy. And by irradiating molecule with laser, we're trying to excite it, while non-adiabatic will compete with it and prevent molecule from being excited. And by including non-adiabatic couplings, one may obtain different pathway of the reaction or slower fragmentation, slower degradation. Did I translate you correct?
You did a great job of
Thank you.
translating, Dr. Kilin.
Do you accept Meade's answer in this translation?
Sort of. Yeah.
Okay, thank you. So Meade, please continue.
Okay. So going on to the next portion, the density or electron density is actually going to be changed with these little time steps, which has been kind of formatted with this equation shown, which is the density with change in time. And this new electron density matrix, which is used to update three things. The three things would be new total charge density, new orbitals and their energies, and then obtain new interatomic forces and positions of the ions. In the case of the increment of density, there are occupation and coherence. The increments of density are occupation and coherence. So the three things that I previously mentioned, which you can still see the figure on this far right, kind of goes into electron density, which would include the density matrix that is change with time. Additionally, with the orbitals derived from the KS or Kohn-Sham equations previously mentioned. This updated density is used with the Kohn-Sham equation again into orbitals and orbital energies. And so then the Hellman-Feynman forces correspond to the occupation and modified total energies, which act on nuclei to change the geometry of the structure. This is then used with Newton equations for motion of nuclei positions, where we have simply mass times the second derivative of the position, which gives us acceleration. In our case, force is a function of electron density, and we can see that the gradients relative to the position, which is the gradient, which is the derivative in all directions, times the total energy of the, once again, total energy, which is a function of the electron density. All of these can be used. All of these are used to change from one screenshot to the next, or from one position to the next. So an example of the end result that we'll be using. So these increment changes are recorded and represent one snapshot of the trajectory. So this is just a figure from previous work that has been done, which would include most of the equations that I had previously mentioned, though this information right here is not metal and ligand. This was just kind of to show you more of like a trajectory as positions have changed throughout the simulation. So we go from 0 and further down the line we go to 1300 femtoseconds, where you can see bonds quote unquote breaking, or nuclear, in our case ionic dynamic parts moving. And this occurs more and more and more throughout our simulation, to the point where we would see degradation or photocleavage with our TDESMD methodology used. So I had previously mentioned how all these steps are really meant to, the figure below kind of went through all of the major ionic and electronic parts. There's kind of some background information that I'm going to explain right now, which are the major assumptions. For example, we're going to be using constant dipole, which is, in our case, the transition between ground and excited state is constant, focusing on high laser intensity. It has a strong, it's based on pulse area theorem with strong field intensity. Surface hopping, a stepwise change in occupation. In our case, we're assuming that the values are simply going from ground state to, excuse me, from 1 to 0 in the ground state. This will be a -1 value, whereas the density matrix going being from 0 to 1 of the excited state would give us a value of +1. And then the fourth assumption, major assumption, which is the domination of dissociative versus dissipative. They dominate. Dissociative process is dominant in the photofragmentation experiments, and then classical path approximations treats electrons quantum mechanically and ions classically. In our case, they're both treated as point charges. Okay. So the main conclusions are that the Kohn-Sham equations were used, additionally with this Rabi cycle or Rabi theory, behind this experiment. So these two were the main initiating, let's say, theories behind what we could have done. Increment of ionic positions was the unique point of our work, whereas a step-by-step change in these ionic positions. Additionally, with the increment of the electronic dynamics, which were used to change the positions, and then quantum mechanically, treatment of electrons as classical points for ions. Once again, we kind of mentioned a large portion of the assumptions that were used, and the main ones being like classical points. Electrons were treated as classical points, such as ions as well. So the end, and I understand it was choppy, but once again, this is my first time trying to speak in theoretical terms, and so it's quite a challenge. So I want to thank you, my advisor, Dr. Rasulev, and Dr. Kilin, for the assistance so far. And I'm more than happy to ask any questions that you guys have typed in chat.
Okay, please join me in thanking Meade for this first theory talk, as he declared it, and let's go forward with asking questions. And David Graupner has a priority to ask if you want to ask something, because David needs to leave in a minute.
So the questions that I had, you asked during the presentation.
Okay, so I was your agent. Okay, are there any emergent questions before we go to the list? Let me ask question to Meade, a provocative question. Like, what would you ask yourself if you would if you write a paper and then you play a role of reviewer? What seems most doubtful for you in this methodology that you have presented? What induces your suspicion, and what you think may ruin trustability of the methodology? Like what
Like,
you
yeah,
what you do not believe in your own presentation?
yeah. The main, let's say, gap is, though I'm reading these equations and what they mean, such as using Wikipedia or textbooks that I have rented from the library, I do not know where and how they are exactly connected to the work that we have done so far. And so I myself am unsure of saying, yes, this is where the Rabi frequency comes in, like right here with this code or with this outcome. So it's my connection with these equations to the outcomes. That is my doubt, I would say.
Okay, very good, very good. So it's basically you are asking questions to maybe those who were practicing these equations before. Yuval, would you like to help Meade and answer his practical question, not generally, but connection between equations and computational methodology? Like, where is the Rabi frequency and how it is related to like, are there any approximations? How one can control it?
I guess in your code in the in-car, you have set NSW, which is a ionic step, right? So you set it to 5 femtoseconds for in-car ground and 5 femtoseconds for in-car excited. So 5 plus 5 is 10. This 10 is just a Rabi frequency.
Yeah.
And we assume that Meade was looking inside the input files, right? Meade, were you in cars?
I mean, yeah, I've seen them. It's just trying to connect it all. Yep.
So in this, thank you. In these simulations, Rabi frequency is a parameter that is not computed by your computational methodology. It is an input parameter that human sets up. And if you want to make it longer, if you need lower frequency, then you increase the period. So you basically use larger number for this NSW parameter. Make sense?
Yeah. I recall seeing the 10 femtosecond mark. Was there a particular reason you chose 10?
Okay. Yeah, let me address it if you doesn't want.
So I guess we previously did some calculations. So the 10 femtoseconds Rabi cycle is approximately consistent with nanosecond laser.
Yeah.
So for some specific experiment, it was adequately representing experimental situation, but generally, the value of Rabi period, which is inverse of frequency, 10 femtoseconds, is very much exaggerated. In most realistic situations, it will have lower value. But on the other hand, if one lowers the intensity of irradiation, then photodegradation that you are modeling will go much slower.
Yep.
Slower than your computer resources allow and slower than your human patience allow. So it is an approximation. So as an approximation, one uses, one tries to use the higher intensity of the laser field than it is in the experiment. But overall, product of the reaction depends not on the absolute value of Rabi frequency, but on the number of cycles. So large or small Rabi parameter, the reaction will respond to how many times it went up and down. And if you want to speed up the calculations, we may increase the frequency and get the same number of cycles in a shorter time. Would you approve this answer? Or there are some corrections?
Yes. So basically, you are just saying the pulse area theorem, right?
Hmm?
You are just saying the pulse area theorem.
Exactly. Exactly. Meade, do you accept our collective answer?
Yes, yes, I do. I remember reading that. Yes.
Okay.
Okay.
Let's check if there are any other emergent questions. Fatima, did you want to ask something to Meade? Looks like no. Amir?
Any question for me?
Yes. Do you have any question you want to ask?
No.
Okay, that's fine. So you think it is logically arranged and everything was clear?
I'm not sure.
Okay, well, you can type it later in the chat line or in the email. Just if something was not clear or not explained.
Okay.
Thank you, thank you. Amir, do you want to ask something? There is a connection between project of Meade and yours because it could be a possible step for your project to see how the polymers will break on pieces upon photoexcitation. Like, was the presentation by Meade sufficient for you to start such calculations? It looks like Amir doesn't have questions. Okay, so let's go through the slides. And I think most questions are from myself, but let's go over the slides starting from the beginning. Yeah, maybe slide 3. So what is the goal of the talk? By the end, we all got some idea, but how would you briefly summarize what was the goal of the talk?
For me to explain the methodology used
No.
in TDESMD.
No. It was right now you are answering as you are a student in a class and you need to pass an exam. What is more globally for you as a researcher, or if you would combine this segment with your previous talk about results and present it on the like seminar? Like, what is the goal of this section of your presentation?
Well, okay. You may have to reword it one more time because I'm thinking of saying, well, this is meant to give you a basic understanding of the process, this particular slide, and it's also to compare with other simulation methods such as regular molecular dynamics, excited state molecular dynamics, and then TDESMD. And I wanted to give a visualization of this process using my left figure and the right figure.
Nothing is wrong, but by the nature of the human nature and nature of scientific community, a lot of activities are competitive.
Yep.
And when you will be writing and submitting paper, there will be specially trained reviewers who will their goal will be to find weaknesses and reject your paper if possible. So one of the goals of your talk was to prove that there is a methodology to describe breaking of molecule on a pieces, and to justify that this methodology is trustable, at least from the logical point of view.
Okay, yeah.
So your goal is to convince audience that if one follows the protocol that you are describing, one would get adequate description of your polymer breaking on pieces.
Yes, that is a very strong and assertive way of thinking about it. Okay.
Okay, and when it will be time to write, please think about it. So
Yep.
it's not you need to convince reviewers who are not necessarily on your side. They may consider you predominantly critically.
Yeah. Yep. That's a very good way to look at it. Thank you.
Okay. Slide 4. You already answered the blue and red populations in this potential energy surfaces. Slide 8. Do you see any typos in the this point third line from the bottom?
Yeah. Yeah. Yep. That I once again was following the paper, so that actually might be from the paper too.
But in your own paper, you may want to retype it.
Yeah.
Can
Yep.
you please
Thank you.
point with cursor what you want to? Yeah. So may I ask you background question? It is not about the method that you presented. It's more general. What your vision of the term self-consistency?
Yeah. Consistency. Well, okay. If relating to the equations, then I don't know. But if relating to me, then I'm inconsistent with this work because I am unfamiliar with a lot of these terms. So, is that what you're getting at with me personally?
Well, the concept of self-consistency is integrated part of this calculations, and maybe you may bring up some positive memories from your previous academic life, or just give interpretation.
Yeah, at the top of my head, self-consistency I'm unfamiliar with, and yeah, maybe it's one of those things that maybe I had it in your class and it's just not ringing a bell. But self-consistency I'm unfamiliar with.
Do not admit it in public because it undermines my teaching.
Fair enough. Okay.
So let's probably we'll continue. We're not about self-consistency. Let's go to the slide 12, and it is not designed to describe what self-consistency is, but it can serve as illustration. So let's discuss first two equations. And would you please explain their connection to each other? Let's assume that delta t is equal 0, so we look no time, we just look for ground state, but redo the equation, first and second equation. what is the connection between them?
Well, simply the electron density is simply put here.
Okay. And
Enough.
where, so first equation, just verbalize what first equation gives you.
The electron density, if in our
Uh-huh,
case he's at time
As,
0,
as function of what?
a function,
Constructed out of what?
a function of electron density, position, and time.
And then next?
For the next equation, or the same?
No, next symbol after.
Yeah, then it would be the orbitals and the complex conjugates of the orbitals
Okay.
of the
So
ground state and the excited state.
Good, thank you. Where do you get orbitals for this first line equation?
They were from the Kohn-Sham equations.
Where is your Kohn-Sham equation?
Very early in my presentation.
No. Once again, what is your second equation?
Oh, okay. It's with the QS equation. It's the updated density with the KS equation too.
So it's Kohn-Sham equation.
Okay.
So starting over from the beginning, first line, you are obtaining density as function of orbitals, right?
Yep.
Where do you get orbitals for the density?
Where do we get orbitals? They were, okay, my previous comment was they came from the Kohn-Sham equation, which was previously mentioned.
Okay, and please use your marker, your cursor to point it. Okay. So from the second equation, you get orbitals, right?
Yes.
And they are plugged into the first equation. Correct?
Yes.
So
as time proceeds.
But how can we plug in the density into the second equation if we didn't solve the second equation yet? Don't you see any logical paradox?
Yes, I do.
So can you explain it by your own words?
One moment. I reserve the right to look at my previous slides for one moment, please. Wouldn't they have been calculated from, I'm going to say the word DFT, slide were we on? Right here. They came from DFT approximations, such as the initial optimization.
In some sense, self-consistency is the heart of DFT. And what you are describing, equation 1 and equation 2, they summarize DFT themselves.
Okay.
But I would like to hear if you observe any paradox with the fact that in order to let's go over. I apologize for taking time, but I want to hear enthusiasm and hear that you recognize this challenge. So starting over, first equation.
Yep.
What do you get? What is expresses?
It's the change in orbitals and orbital energies from excited.
It gets density. It gets density as function of orbitals, right?
Electron density is a function of orbitals. Okay. Yes. Yes.
Where do you get orbitals for the electron density?
Well, it depend. I know you're saying at time 0, and what I had previously had mentioned was DFT from the initial approximations. So I understand that there's a paradox if we were to use this second equation because we're at time 0. So it has to have been initiated from some point.
Exactly. Okay.
Yes.
You recognize the paradox.
Yes,
and
I do.
Then after you practice first equation, you plug in this rho, this density, into the exchange correlation potential, into the potential that can you please mark, point it with cursor, this V and then a rectangular bracket. Yes. So this rho from the first equation comes into the second. But it is the question like what was appearing earlier, a chicken or an egg?
Okay. Yep.
So they are interconnected. And it is a true mathematical challenge. So you cannot write these two equations and mathematically solve them just by pen and paper. And the only way to solve them is to make some initial guess predominantly wrong. Use it as an initial guess for the rho, plug it into the second equation, find orbitals, and then use this orbital to practice equation number 1 over again. Then recompute density, plug it into the second equation, find new orbitals, and then repeat the cycle again and again.
Where in our code would this be happening?
It's happening anytime you are practicing density functional theory, which is part of your methodology.
So it's just whenever we're using, let's say, molecular dynamics with the in-car, post-car, puck-car,
Yes.
it's throughout our process. Okay. Because that's the underlying theory of what's happening. Okay. Okay. Okay.
Cool. And the only difference from regular Consham is that this rho ij is not for the ground state, but for the excited state, which you modify in the in-car. Okay.
So I have a question with you, Dr. Kilin. So I've actually rented a handful of books from the library, specifically going over DFT.
Uh-huh.
And so do you have any particular recommendations on books that would be best to read about this?
Yes. Parr and Young.
Okay. I will, let's say, use this and maybe order a book with them, because a lot of these books, they're just pretty jumpy. And so it's difficult to follow along. And I know it's necessary for this work, and I'm trying to read an hour or 2 a day. So I will look into that. That's just the authors?
Yes.
Do you remember the
and title will be something standard like density, like review of density functional theory, or nothing special.
Okay. Okay. Yeah, I know a lot of or do you have any more comments as of right now?
No, I think we did cover everything that was typed. Well, you're going to say something, but it's if Aaron wants to ask any questions or point Meade to any inconsistencies, please use the chance. And Meade, you were starting to say something.
Yeah. Yes. So admission of weaknesses in research, I have learned it may not be the best, but this is practice. And so I know a lot of where my flaws are, and is there a way to present this type of information better? Because it is so detailed that you want to see the equations, but the equations are also very difficult to kind of explain. So do you have any advice on how to present this information?
There, you do want to, Aaron, after I'm finished answering to Meade, you have a chance to ask if you want to. So Meade, you are looking for a shortcut?
No. I've like I said, I've never presented this stuff before. Like I've never tried to do this. So.
But even if you do not want a shortcut, I do have one in mind.
Okay.
It is not immediate.
Okay.
So you already did a great job presenting today. Maybe after, as a follow-up of your presentation and discussion, you can add corrections to your slides, and even maybe present it at some other meetings or as a portion. But when it could be a really great idea if you just type everything you think and understand about this procedure. But when it will be time for actual paper, we will take whatever you write and shorten it to after making it more brief, there will be less chance to make an error. But right now it is an important practice so that you observe internal connections between components in these calculations, and you will be able to build a skeleton of your narration for the paper. So later on, there something will be removed from the story for the sake of brevity. But right now it is a very important practice, because if we remove it right away from the beginning, there is a chance that we will be doing things that we do not understand.
So a quick question. Thank you. Have you had to present this in a PowerPoint format, or is it simply through paper?
Do you want to borrow slides?
No. I'm saying this in a sense of this, like I said, it's so foreign to me to just look at equations and kind of explain those. So the question to you is this very consistent in the computational field, where, let's say one PowerPoint to a group of other doctors, you have legitimately just gone through the methodology of TDESMD?
What you did is a very standard practice.
Okay, a standard. Okay, fair enough.
Standard practice, and it is there are two communities: community of method developers and community of applied scientists. They do overlap, but in the applied research there are more like figures and graphs, and in method development there are more equations. But typically there is a combination of both.
Yeah.
And, it is a very natural, healthy, and standard practice to go over a set of equations. And there are a lot of communities where it is very appreciated, and people. I had a lot of colleagues, mostly senior colleagues, who fall asleep when it goes to figures and graphs,
Okay.
and they wake up and start following literally each symbol when there are equations.
Interesting. Yeah, that, theory versus the application is the bridge that I need to connect better to. So that's just more practice for me.
Okay. But it's a really great start, and when there will be time for you to present at some other forums, your, I don't know, departmental seminar or other things, feel free to include these slides or updated version and practice it once again.
Yes,
Especially presenting it to unbiased audience who have no idea what you're doing. It's a really good practice.
Okay.
Yes. You were saying something? No?
Okay. Well, yeah, you know, you wanted to know my enthusiasm, Dr. Killen. I'm very enthused. I'll even yell if you want me to. But you know, once again, this is just you know, I tend to have experience in the polymer field, and now I'm looking into computational stuff, not QSAR related. And so every new, let's say, project I'm doing is a whole new world to me. And so I tend to be the underdog consistently. And I'm trying my best to be up there with you, you know,
You're doing good. You're doing good.
to keep going.
It is a standard practice in graduate
Yeah.
school that you are getting challenges every day.
That's right. And I'm excited to do it with you, Dr. Killen, and Dr. Rasulev as well, if he's still in this chat room. It's just, you know, you got to climb the mountain, and I'm climbing it, okay? So don't worry, there's excitement here. You got enthusiastic students, okay?
Sounds great. Aaron, did you develop any questions or critical comments towards Meade and his story?
I just had one question. Could you go to the slide where you show the Rabi cycling? It was a different slide. It was where you had the figures of changes in occupations.
Changes of occupation.
So like the EE and
slide number 4.
Oh. Yeah. Or is it the next one?
Next one.
This one.
Yeah. So you went over the solid lines, like the red and blue, but there are also dotted curves in the figure as well.
Mm-hmm.
So what are those, and do they matter at all for like the study or the system that you're studying for photo decomposition?
One moment, please.
Thank you, Aaron. I value the question.
Well, they do matter. The dotted lines, such as the purple one, indicate coherence. So, 1 second. Okay, so relative to each other, the red and blue blue lines represent diagonal elements of the density matrix, whereas the purple and the yellow represent off diagonal. Now, with our approximations that we've mentioned, we are focusing more on the diagonal portions of our matrix rather than the off diagonal elements. That's what they mean. Would you like any further detail?
So I guess, how do I want to say it? So these figures that you plot, they're for assuming that temperature is 0. But if you included temperature, I guess they kind of tend to disappear. So for your simulations, it's like you can neglect them because you're studying decomposition at high temperatures, so they dephase very quickly. I guess that's my understanding anyway.
Can't say temperature, but we could say, you know, energy inputted. obviously we're trying to put in energy in the system simulating like a light wave, right? Or rather than a heat, which is like you slowly raise it up, and then if you want, you can drop it down or something. So I
I
guess
guess
the difference would be like how the energy is incorporated into the system.
right. I guess what I'm trying to say is that so like for this B panel, it's like it assumes 0 temperature for this figure, but if you included temperature, it's like this yellow curve would eventually dampen to 0 over time.
I'm unsure. And I guess in our case, since we're not considering them, whether they're dampened or not is not what we're focusing on. It's not being incorporated in our
So
approximation.
let me translate the question of Aaron, which makes a lot of sense, and it originates from the advanced PChem 767 that Aaron took some time ago. So I will translate question of Aaron into the language of nuclear magnetic resonance, where Meade can later practically privately consult with Professor Rasulev. So in the nuclear magnetic resonance, there is a free induction decay. So upon exciting, removing this two-level or multi-level electronic system from equilibrium, it will return to equilibrium determined by T1 and T2 parameters, and which is like relaxation and dephasing. In this modeling, right now in the both figures B and C, the T1 and T2 relaxation and dephasing are completely neglected. So it is assumed that there is no relaxation and no dephasing. And Aaron is picking up the big spot, telling that in any realistic situation, neglection of relaxation and dephasing should be treated with special care. So in Meade, in your presentation, you already mentioned that non-adiabatic couplings are neglected, which means there are no relaxation. And Aaron pointing on the fact that in addition to relaxation, there is a dephasing that affects off-diagonal elements, and it happens even in absence of non-adiabatic couplings through the ensemble average and random fluctuations of energies. So, Aaron, did I translate your question adequately, or you were meaning something different?
No, I think that covers it.
Okay.
Yeah, I guess it was hard to follow. I apologize. I guess this is.
So I'll summarize, and I'm trying to record. Probably it will be available for you need to watch and listen if you're interested. So we have to recognize that we are walking on a very thin ice. This is quite challenging calculations with a balance of approximations, and
Yep.
if they allow to predict something realistic, it is a very big luck and coincidence of several factors. And it is very easy to find that the method is missing one or another important factor. And it needs to, like, when you will be writing about it, you just need to recognize it so that it is like delicate balance of effects. And
Yeah. So
Educated reviewers will come after authors and ask why one effect is taken into account and another is not, and how to justify certain approximation and neglection of certain effect.
Yeah. Okay. I can. It's my verbiage would say, can we rationalize, these approximations, for example, excluding the off-diagonal elements of the density matrix. So I think the way you're wording something is I should just be concerned that I'm wording it properly and we have the approximate or the correct rationale, or excuse me, adequate rationale to be able to do so in explaining such details.
Let me try to answer to Aaron myself. So, as I interpret your question, Aaron, you are telling that since in all realistic systems there is a dephasing, maybe one can neglect off-diagonal elements anyway, as a provocative formulation.
Yeah, because I guess dephasing usually happens like on the femtosecond time scale. So you'd have to be dealing with fast chemical processes that compete with it.
Yes, I admit this provocative question, but time of dephasing is applicable. Consideration of time of dephasing if the system is instantaneously promoted to excited state and then is left alone to evolve forward in time. Here it is a different regime. The system is constantly being irradiated by light, and the light irradiation creates phase continuously. So this phase doesn't have time to disappear. It's not, a system is never left alone. It's being perturbed by light continuously. And this, if we would do absolutely correct, ideal and precise theory, we would include this off-diagonal elements and they will be there on one hand. But on another hand, it is very adverse practical approach to take into account these coherences. They will make any calculation much slower and non-practical. So if we keep understanding that there is a very strong inducing electric field and move from the panel B to panel C, right now I'm intentionally answering to Aaron, then you do see that when the light is on, when the pulse is coming through, the when the pulse is non-zero, ground and excited state exchange their populations, and off-diagonal elements, coherences, get non-zero values only while pulse is on. When the pulse is over, off-diagonal elements disappear naturally. So if we make an approximation that our molecule is irradiated by train of short pulses, then during the time when pulse is acting, one admits there are off-diagonal elements, but we assume that this duration of the pulse is so short that we just look configuration before and after the pulse, when ground and excited states are swapping their occupations. In between pulses, when the green, there is nothing green. There is only fully occupied and fully empty states, which are really comfortable to describe and to use for computing interatomic forces. Does it, do you admit this comment?
Mm-hmm.
Okay. Whew. I think it was
the only volley I would have back is that. Like,
once again.
so if I wanted to, like, hit the tennis ball back onto your court, I guess this would, your panel C assumes 0 detuning.
Yes.
So if there was a slight detuning, and then that would give a little bit of resonance, or it would give some off diagonal elements, right?
Correct.
If it was, but yeah, if you assume 0 detuning, then they completely disappear.
You are correct that with slight detuning, there will be incomplete transfer from ground to excited, and there will be some leftovers of the off-diagonal elements on one hand. But on another hand, if detuning is a little bigger than small, then there will be no interaction at all. So if one looks onto extreme cases, one can consider full detuning and no full resonance and no resonance at all. If there is a full resonance, it's complete transition of population. If there is no resonance, then system is not interacting with electromagnetic wave. And again, it is walking on a thin ice for the reason that more detailed consideration will boost level of complication and numerical cost exponentially, with all effects taken into account. So by good luck and by this balance of approximations, there were several successful interpretation and prediction of experimental outcomes, but it is a thin ice.
Okay, that makes sense.
More questions? More points to discuss? If
I just have just a comment, as an impression, like a few impressions, like concluding that stuff.
Please.
So mainly it's of course I'm understanding it's to Meade. First of all, yes, Meade, you did a good job putting together all these the equations, methodology, just to explain that thing. Yes, I understand for you it was somehow complicated since it's completely theoretical stuff. Yeah. But from another thing, I'm a little bit concerned since for you, when you was putting that together, for you it was kind of completely disconnected, this theoretical part from the work what you was doing, right? That's not good, because when you was putting that together, at least you had to ask questions from Dr. Kilin, Dr. Yulun, or me in some of the ways to understand it more before you was making this presentation. That would be much better, and you could understand much more, and we would spend much less time on explaining some really simple things in some of the cases. The third impression that you probably put all these slides together like in the last moment, because in some cases, it was even a little bit difficult for you to explain some of the things. So that's my three impressions. Yeah, you have to be next time really well prepared, ask questions before the presentation and not discussing all these simple things during the presentation. That would be much better and really help for you in terms of better understanding what is behind of that work, what you've done, and what the theoretical background of that. Yeah, so that's what I wanted to say.
Yeah,
Yeah.
I'll definitely be able to do better next time. Thank you.
Mhm. Thank you, Professor Rasulev, for important comment. And ideally, it would be on the echoing your comment. It will be really beneficial for Meade to combine his previous talk and today's talk into one and present it instantaneously, both theory and results as a one segment. It will definitely be appreciated by audience. It will make connections while preparing this presentation, and it will be better chances to just run through the components of the through different slides by answering, like using computed results to illustrate equations and use equations as background for any questions about practical results.
Yeah, I also think that would be good to put these two parts together. That kind of will make it much smoother, going through the work. Yeah, and well understandable in some cases while we're doing this, and where originates that particular thing. Yeah, would be definitely beneficial for me, for us.
Okay. And Professor Rasulev, please, if you have few minutes, please stay after we announce the adjourn. We'll discuss on these lines a little more.
Okay, yeah, no problem.
Okay. Okay. So if there are any other questions or suggestions, please use this forum to declare them. If no, let's thank Meade once again. So if there is a necessity to talk one by one, just send me a brief message. I will reconnect in whatever half an hour. We'll do one by one meeting if anyone needs it. Next meeting, there will be a presentation by Yulun on hydrogen sulfide, new project. And with this, let me announce the meeting complete. So many thanks for joining, for questions, discussion.